This is an exciting day, and this is an exciting lesson because this is the first official lesson of geometry. So we're going to start with a conversation about patterns and inductive reasoning. So before we get into the lesson, I'm actually going to introduce some things. So I just want you to listen, and if you want to take notes on some of what I say, that would be fine. But geometry, most of you geometry, and the geometry that we're going to study is Euclidean geometry. And Euclidean geometry is named after an old philosopher from about 300 BC named Euclid. And what Euclid did was he basically looked around in the world and he noticed some patterns. Like we talked about, what mathematicians do, we talked about at the beginning of the year. They do three things. Mathematics is the study of patterns and relationships. And mathematicians, they recognize patterns, they describe patterns, and they generalize patterns. So that's exactly what Euclid did. And Euclid looked around and he noticed a lot of patterns. And when he noticed a pattern, he would basically test that pattern. And after testing that pattern, if it stood the test of all of his tests, and he was able to figure out that it was true in all cases, he would actually make them rules, and those rules have special names. He called them theorems and postulates. And these are the set of rules that Euclid came up with that basically define what geometry is and the rules that we use in a lot of math for geometry. And we're going to be doing a lot of that as well. Most of geometry is very intuitive. It makes a lot of sense because how it was discovered wasn't like someone was just pulling out of thin air making up these rules. They were just looking around at the world around them, noticing things, and then trying to describe it using math. For example, let's take this pattern here. Here we have one circle. Then we have three circles. We've added a row, and in the second row we have two circles, and here we've added a row again, and I think you can see where the pattern is going. We're adding a row each time, and every time that we add a row, we add one circle to that row. So our last picture here should look something like that. And that's obviously a little bit messy, but you get the idea. Well, this is an example of a pattern using shapes. There are all types of patterns with numbers, for example. Let's see if you can figure this pattern out. We start with 1, and then our next number is 2, and then our next number is 4, and then 8, and then 16. And what you may notice here is that every time these numbers are doubling. So here we have 1, and then 1 times 2 is 2, and then 2 times 4 is 4, and then 4 times 2 is 8, and then 8 times 2 is 16. And then 16 times 2 would be 32. 32 times 2 would be 64. And 64 times 2 is 128. And so some of you may have seen that pattern right away. This would be the pattern that we describe, and we could keep going, but we won't. We'll just leave it at that. And this is one way you could represent this pattern, but I want to make this point here really quickly with this example. There are actually lots of ways to represent this exact pattern, and I'll show you one more really quickly. If you just keep going on and you just keep doubling this, you'll get to this pattern. But what if we don't think about doubling it? What if we think about just writing it in a different way? Can you think of another way to write, I don't know, let's just think about 2. Is there another way that you could write 2? Well, there are lots of ways that you could write 2. I'm going to write 2 as 2 to the first power. Okay? Is there another way I could write 4 that looks similar to this? Yes, 4 is also 2 to the second power. And 8 is 2 to the third power. And 16, guess what, is 2 to the fourth power. And then as you could see, this would be 32, which is 2 to the fifth. 64, which is 2 to the sixth. And then like we said earlier, this one's 128, which is 2 to the seventh. So 1 is actually 2 to the 0th power as well. So I just used this example to show you that just because we can recognize that these are doubling every time, that doesn't necessarily mean that's the only pattern that I can use. There's almost always two ways to represent a pattern, and this row on top would be another way to represent this exact same pattern. So let's keep moving. Let's see what we can do here. 3, 8, 18, and 38. Do you see the pattern? Well, if you look more closely, let's look at what the difference between each of these values is. The difference between 3 and 8 is 5. So I'm just going to write a little 5 right there. The difference between 8 and 18 is 10. And the difference between 18 and 38 is 20. So what do you think would be next? What would we do? Well, there's actually a few ways that you could go here. That you could see that maybe the difference between each of these numbers is doubling. So first we had 5, and then the next difference was 10, and the next difference was 20. So the next difference should be 40, which would make this 78. And then the next difference would be, what's 40 times 2? 40 times 2 is 80, which would make that 158. And then next difference would be 80 times 2, which is 160. And the difference between, if we add 160 to 158, then we would get 318. Okay? So this pattern would continue. There might be another pattern that you could have seen here. And I've seen other students come up with different patterns than just this one. And that is totally okay. Just because we see one pattern or the other doesn't mean that this is right. Just because this is the pattern that I saw doesn't mean that this is the pattern that everyone saw. When we're recognizing patterns, it's not really like there's a right or wrong pattern to recognize. It's more of just that this is one of the patterns that I see. For example, here's what I want you to do. I want you to take this pattern and I want you to try and think of multiple ways that you can represent this pattern. First, figure out what the pattern is, if there's a pattern, and then go ahead and fill in what you think this might be, and then see if there's another way that you could represent that exact same pattern. So I want you to pause the video and do that for just a second. Okay, now that you've come up with this pattern, let's take a look at a couple different patterns here. This one's a little bit more difficult, but here's the pattern that I see. I see that this is 1 is the same as 1 squared, and I see that 4 is the same as 2 squared, and I see that 9 is the same as 3 squared, and I see that 16 is the same as 4 squared. So if I continue this pattern, I should get that this is 5 squared, which would be 25. I should get that this is 6 squared, which is 36, and I should get that this one is 7 squared, which is 49. Now, some of you may have seen that pattern, and that's great, but others of you may have seen a different pattern. For example, what if I looked at the difference between each of these numbers? The difference between 1 and 4 is, of course, 3. The difference between 4 and 9 is, of course, 5. And the difference between 9 and 16 is 7. So if I continue this pattern, then the difference between 16 and the next number should be 9, and 16 plus 9 is 25, and the difference between that and the next number should be 11, which is 36, and then the difference between that number should be 13, which would make this 49. And look, if that's how you saw this pattern, look, we actually get the exact same numbers. So isn't that interesting? We have actually a couple of different patterns that we're seeing here. These are all of the squares. So we have 1 squared, then 2 squared, then 3 squared, then 4 squared, then 5 squared, then 6 squared, then 7 squared. But what we're also seeing is that, hey, the difference between each squares as I go up is just increasing by 2. So the first difference between the first two squares, 1 and 2, is 3, and then the next difference is 5, and then the next difference is 7, and the next difference is 9, so on and so forth. I wonder how far that would go. If we continued, I wonder how far that would go until if we kept going, if that would we would get to more and more squares, if we would discover more and more squares that way. Maybe so. And then there's one more example on here. And once again, this is just to show you that this could go a couple of ways. And there's not necessarily one correct answer when you recognize a pattern. There's almost always a couple of patterns that you may recognize. And so here, 4, 16, what do you think goes next? Well, 16 is 4 times 4, so maybe I'm supposed to multiply this by 4 and get 64. Also, what's the difference between 4 and 16? That's 12, so maybe what's next is for 16, maybe I'm supposed to increase everything by 12 every time, which would make this 28 instead. Once again, I just put this example in here to show you that just because you see a pattern doesn't really mean that it's necessarily the only pattern that you can see, and there's almost always multiple patterns that you could create. This is not about getting the right pattern. This is just about practicing, exercising that part of our brains that is to recognize patterns, which a lot of us, if we convinced ourselves that we're not very good at math, will probably have had shut off by now. But there really are patterns all around you. And so we use a couple of terms to be able to describe those patterns, and those terms are below. Those terms are conjecture. And I want to define what a conjecture is, and I want you to write this down, and this will also be on your definition sheet. But a conjecture is basically an educated guess based on observation. That's way too big, so I'll make it a little smaller. It's basically an educated guess based on observation. If we look at the definition of conjecture on your definition sheet, it should say something similar to that. And basically, when we make a conjecture, we're not making a rule, but we're saying, hey, here's a pattern that I'm seeing. Just like this. A conjecture would be that, for this first one up here, a conjecture would be that the pattern is that it doubles by 2 every time. And then inductive reasoning. This is basically just a process. Let me see if I can get this to work. A process of making conjectures and recognizing patterns. When we are using inductive reasoning, we're looking around us and we're trying to recognize patterns, and then we're trying to use those patterns to describe. So this is kind of just an intro on patterns and on inductive reasoning. What we're going to do now is we're going to take a couple of examples of conjectures, and we're going to dive into that a little further.